Besides relations from a set X to another set, relations from any set to itself are of special interest. They are known as binary relations on a set. This means that a relation on X is a subset of the Cartesian product X times X. Let's look at an example. How do we answer this question? The objective is to collect all ordered pairs that fulfill the condition X less than or equals to Y, where X and Y belongs to the set 1, 2, 3 and 4. We can start with the element 1 in X. Next, find its pair also in X that fulfills the condition X less than or equals to Y. 1 can be paired with 1, 1 can be paired with 2, 1 can be paired with 3, 1 can be paired with 4. This means that the ordered pairs 1, 1, 1, 2, 1, 3 and 1, 4 are elements of R. The other elements in R can be found in a similar manner. Hence, the answer to the question is a directed graph or digraph is a pictorial representation of a relation. In a digraph, each element of the set is represented by vertices, dots or nodes. The ordered pairs in R is represented by an arrow or an arc. There are several properties that can be used to classify relations on a set. Some of the important ones are as follows. Reflexive, antireflexive, not reflexive, symmetric, antisymmetric, not symmetric, transitive. Let's look in detail at the properties of reflexive relations. R is reflexive if the ordered pair X belongs to R for every element of X. The digraph of a reflexive relation has a loop at every vertex or node. R is not reflexive when the ordered pair X do not belong to R for all X in X. The digraph of a not reflexive relation do not have any loops at all vertices. R is antireflexive when the ordered pair X do not belong to R for every X in X. The digraph of an antireflexive relation has some loops at the vertices. Sometimes, in some relations, an element X is related to element Y, if and only if element Y is related to element X. These types of relations are known as symmetric relations. The digraph of a symmetric relation has the property that whenever there is a directed edge from A to B, there is also a directed edge from B to A. If there exists an ordered pair X, Y that belongs to R, but the ordered pair Y, X do not belong to R, then R is not symmetric. In the case of not symmetric relations, there will be some edges in the digraph that only have one directional arrow as follows. A relation that has the property that, whenever an element is related to a second element, then the second element is not related to the first element, is called an antisymmetric relation. The digraph of asymmetric relations only have arrows in one direction. A relation R is called transitive if whenever X is related to Y, and Y is related to Z, then X is related to Z for all X, y and z in X. The digraph has the property that, whenever there are directed edges, from X to Y and, from Y to Z, then, there is also a directed edge from X to Z. R is not transitive, if X is related to Y, and Y is related to Z, but X is not related to Z. The relation represented by digraph G2 is not transitive, because we can see that, 1 is related to 2, and 2 is related to 3, but 1 is not related to 3. Let's look at an example. The following is a relation, R, defined on the set X, whose members are 1, 2, 3 and 4. Is R reflexive? Observe that R contains all elements of the form X, X, namely 1, 1, 2, 2, 3, 3, and 4, 4. Hence, R is reflexive. Observe that, for any pair, X, Y, belonging to R, the pair, Y, X, does not belong to R. For example, 2, 3 belongs to R, but 3, 2 do not. This means that R is anti-symmetric. To check for transitivity, we have to look at pairs of the form X, Y, and Y, Z, and check whether X, Z, is in R. For example, 1, 2, is in R and 2, 4, is in R. Observe that, 1, 4, is also in R. After doing this, for all the ordered pairs in R, we can conclude that R is transitive. We often use relations to order some, or all elements of sets. For example, the relation less than or equals is used to order the set of integers. Relations on a set X, that are reflexive, antisymmetric and transitive, is called a partial ordering, or partial order. Let's look at the following example. We can verify that R is reflexive, transitive, and antisymmetric. Hence, R is a partial order. A set X, together with a partial ordering R, is called a partially ordered set, or poset, and is denoted by the ordered pair X, R. Elements of X are called elements of the poset. Let X, R be a poset, and let X, Y, belongs to X. If the ordered pair, X, Y, or Y, X, belongs to R, then X and Y are comparable. If both ordered pairs, X, Y and Y, X are not in R, then X and Y are incomparable. Let's look at an example. Observe that 1 belongs to X, and the pair 1, 1 belongs to R, hence, 1 and 1 are comparable. 1 and 2 belongs to X, and the pair 1, 2 belongs to R. Hence, 1 and 2 are comparable. Next, we have 2 and 3 belonging to X. However, the pair 2, 3 and 3, 2 both do not belong to R. Hence, 2 and 3 are incomparable. If every pair of elements in X are comparable, then, R is a total order on X. For example, if X is a set of all integers, and R is defined as the relation X is less than or equal to Y, then, R is a total order on the set of all integers. R is a total order because, given any two integers A, or B, we can determine whether A is less than, or equal to B, or vice versa.